be talking about Dissipative Bethe Ansatz, which is a work I did together with Berislav, Cameron Booker, and Dieter. So maybe a more precise name, but not sounding as good, would be Bethe Ansatz applied to systems experiencing loss. So let me first start by motivating why we were interested in trying to address this question and get some analytical results for such systems. The main motivation comes from cold atom experiments, such as quantum Newton's cradle experiment, which I'm sure all of you have seen on many occasions. And more recently, there was also an experiment on a chip where they were able to see the emergence of GHD. So these are experiments working on integrable systems. And the main source of errors in these experiments, if you can call them errors, well, in some sense there are errors because they are quantum simulators, is loss of particles. What can happen is that particles escape from the optical trap through different mechanisms. Either the trap is not strong enough, so it can just not hold cold atoms within, or what can happen is that when two particles meet each other, they get excited too much and we effectively lose them. So the basic idea is to look for particle loss mechanisms which preserve integrability, and also to study, since already the motivation is such, whether they can exhibit interesting physical properties which could potentially be observed in these experiments. So, in order to explain the basic setup, I'll first present the Limblet equation, outline some previous results, then move to a general approach, and finally focus on a particular example which exhibits some, I would say, quite interesting physical phenomena. So let me start with Limblet equation. So if you have some system that's weakly coupled to environment, and if environment is very quick, so what's happening in the environment happens on much shorter time scales than what's happening in your system, and coupling is weak, then such a system can be modeled by Limblet equation, which is described by Liovillian, acting on density matrix comprised of two parts. So the first part is just the ordinary unitary time evolution of density matrix, and the second part describes the interaction of our system with the environment through Limblet jump operators. So there is a particularly useful representation of Liovillian, which can be obtained through so-called channel state transformation. So this is a very simple bijection where basically you take the operators, which can be of course expressed as some, not projectors, but composing of cats and brass, so projecting from a particular state to some other state, and just by inverting this bra into cat. So via this transformation, Liovillian can be represented on these double degrees of freedom, basically just by taking tensor products of H, so because Hamiltonian multiplies this row from left, you put H here, and on brass it acts as identity, and similarly for all of the other terms. So the only term that is connecting the two copies of the system is something that we call the jump term. So the Liovillian can be decomposed into two parts. One is a non-Hermitian Hamiltonian part, and the other one, as I already mentioned, is the jump part. So the non-Hermitian Hamiltonian part consists of the sum of two independent terms. What I mean by independent is that one is acting only on one copy of the system, and the other one is acting non-trivially only on the other copy of the system, where besides the original Hamiltonian, we just set L dagger times L, where L are different Limblet jump operators. So this corresponds to, for instance, putting together this term and this term. And then we have this jump term, which connects two copies. So what do I mean by loss of particles? By assumption, basically, there is some quantity in the original system which is conserved. So if it's U1 quantity, let's say magnetization, particle number, we just refer to it as particles. But it doesn't have to be a U1 conservation law. It could be any conservation law. So what is important is the following. So it should commute with the Hamiltonian, and all of the jump operators, so all of L mu's, should decrease the number of this quantity in the system. Or to express it mathematically, they should be eigenoperators of ADM, where M is a conserved quantity, because this means that if you take some eigenstate of M, or some state with well-defined amount of M, and apply L mu to it, then it maps this state to another eigenstate of M with appropriately decreased eigenvalue. Okay, so this is what I mean by loss of particles. So this is the requirement. Okay, so let me just flash through some of the results, which are not just for systems exhibiting loss of particles, but are for general open integrable systems. So there are a lot of works by Tomáš Prosin and collaborators. You'll hear about an example later on by Leonard. So basically in this myriad of works, what Tomáš and collaborators were able to do is to construct steady states for many such systems exhibiting, systems that are coupled to environment, usually just at their boundaries. So you have some particle influx at some boundary, and you're taking particles out at the other boundary. Then there is a method of third quantization, which is a method for solving free systems that are exposed to environment. And again, there are some conditions for Limblet operators for which you can still solve the full spectrum. Then there is an article from 2016 by Medvedeva, Fabian Isler, and Tomáš Prosin, where they solved the free model with dephasing. And finally, this year, there was some work where dephasing was introduced into GHD, where basically you're not coupling, your Limblet operators are not coupling to particular sites, but are coupling to full hydrodynamical cells. Okay, let me move to the method. So, as I explained before, the Limblet is decomposed into two parts. So the first one is the non-Hermitian Hamiltonian, and the second one is the jump part. So one thing that should be stressed is that actually, due to the form of these Limblet jump operators, also the non-Hermitian Hamiltonian commutes with previously defined particle operator, because L mu decreases the number of particles and L mu dagger increases, so if the product leaves it invariant. Due to the particular structure, I will be able to demonstrate that eigenvalues of Liovillian are actually equivalent to the eigenvalues of the non-Hermitian Hamiltonian part of Limblet. So this is due to the triangular structure, in particular because H commutes with M, where we have defined M as a sum of M's, so some particle sums on both copies. Let's say if you have Heisenberg model and M can be magnetization, then this is just magnetization on one leg of the chains, so acting on brass, and this is magnetization that's acting on cats. And this is the super operator that commutes with a full non-Hermitian Hamiltonian. So let's assume that we diagonalize this Hamiltonian and then order its eigenvalues with respect to the values, to the corresponding values of this charge. If we do this, it's not hard to demonstrate that the elements of D, so of jump operators, all lie above the diagonal. And this is simply a consequence of the fact that D, it's here. So this composed of the tensor product of L mu's, and L mu on each space decreases the number of M, which means that it maps the eigenstates of M to the lower eigenstates of M. So it will only have off-diagonal terms, and they will all lie above the diagonal. So this immediately implies that the spectrum of L and H are equivalent, because the only part that differs lies above the diagonal, so characteristic polynomials are equivalent. Furthermore, this means that the decay rates are just eigenvalues of Liovillian, are comprised of the sum of two decay rates of like smaller non-Hermitian Hamiltonian, which act only on bra or on cat. So instead of having to diagonalize full Liovillian, which corresponds to diagonalization of matrix of the size 4 to the L, we have to diagonalize just this non-Hermitian Hamiltonian, which has a size 2 to the L. So already here we have achieved a significant simplification. Furthermore, if H tilde is integrable, we can of course obtain the full spectrum of Liovillian just by diagonalizing H tilde. But eigenvectors of L and H do not coincide. So in principle, one has to perform Gaussian elimination, and finding some way to actually obtain them in some kind of, integrable setup is still missing. But what we are able to obtain are the eigenvalues. So let me now turn again to more applicable things. So the question is, what kind of systems this general setup can describe? Well, usually, basically in any system, you usually have some U1 conserved quantity. Okay, if you're considering XXZ, not XYZ. And then L mu, you can choose just a single site lowering operators, which correspond to losing your cold atoms, which are simulating your XXZ spin chain at each side of the chain. And in this case, H tilde actually corresponds to adding to Heisenberg Hamiltonian, say, the imaginary external field. But the same thing can be done for Lieb-Liniger model, where you would just add external particle number operator, Hubbard model, Heisenberg, and so on. So the second setup is when you introduce the loss of particles just at one boundary or at both boundaries. So in this case, H tilde actually corresponds to taking Heisenberg XXZ model by adding some non-zero chemical potential or external field at the boundaries. And this can usually be solved via Sklianin's reflection equation. Then there are also two-body losses. So if you can imagine when two particles scatter, they can kick each other out of the system. And this usually map to imaginary interaction. For instance, if you are considering Heisenberg model, this would correspond to imaginary delta Heisenberg model, or Hubbard imaginary U, and so on. Okay, so let me turn to the example. So we decided to study the simplest example we could find, which is just taking Heisenberg XXZ model and adding a single loss at the left boundary. Okay, so the non-Hermitian Hamiltonian, from which we can obtain the full spectrum of the corresponding Liovillian, looks like this. So everyone probably knows that this can be solved via Sklianin and obtaining Bethe equations and so on. So the question is, what kind of physical questions can we now address? So the first question that usually people are interested in is what the steady state is of such a process. And in these systems, the steady state is usually trivial because you're taking particles out of the system. What you'll be left with at the end is an empty system. And in this case, it's just all spins down state. So the second question is, what's happening after a long time, but not infinite time? So basically, what is the state that survives for the longest in the system? And it's, so this property, or the real part of the decay rate, the leading decay rate, is called the Liovillian gap. And in particular, its scaling with the system size n tells us something about transport properties in these systems after long enough time, and so on. So there are two regimes, and this question can be addressed very simply. One doesn't even need integrability, because it's the solution with the smallest eigenvalue lies in the single Magnon sector. So for delta smaller than 1, one can show that the gap scales as algebraically with the system size, and for delta larger than 1, the gap scales exponentially with the system size, and these are explicit expressions. Yeah, maybe more interestingly, okay, this is just a numerical verification of the gap scaling with the system size. But maybe more interesting questions are what happens out of equilibrium. So if we start from some initial states and look at the dynamics, and the first thing that we observed is that there is discontinuity happening in the Liovillian spectrum. And it happens for single Magnon sectors as well as throughout the spectrum. So what are the physical consequences of this phase transition? There is one particularly interesting instance on which we can focus, and we'll see that the consequences are quite severe. So instead of looking at all spins down state or excitations on top of that state, which is the ground state, we can instead look at what happens if we start with all spins up state. So we have a chain that is completely filled with spins, and we put the spin sink and a single site and look at what's happening. So in order to study what's happening for this state, we should study excitations on top of this state. So these we call top Magnon sectors, because U1 symmetry is broken. So there is a difference between looking at excitations from the vacuum or from the most excited state. And what we've observed is that depending on the value of gamma is coupling to the environment, but for small gamma we observed that there is a phase transition, so these are decay rates, happening always at delta equal to 1, but that's true only for small gamma. So there is a discontinuity in eigenvalues. So what we then looked at is starting from this state, creating excitations, basically diagonalizing the matrix and looking at eigenvalues in different at smallest eigenvalues in different Magnon sectors, which tell us how long does it take, let's say, for all states which have all spins up except for one which is turned down. So for all of these states to empty out of the system, or all spins up except for 2, and so on. So these are top Magnon sectors. And what we've seen is that, as we increase the Magnon sector, the decay rate starts approaching 0 for delta larger than 1. And actually, these solutions, the slowest solutions, correspond to the boundary bound states. So they correspond to the states that are bound at the left boundary of the system. And for them, we can solve explicitly for their decay rates. But what can we learn from this? Well, as I said, the slowest decay rates will tell us how long it will take for, let's say, all spins up except for such states to empty from system, all spins up except for 2, and so on. And what we were able to show is that as Magnon sectors are increased, the real part of the eigenvalues goes to 0, and it approaches this point exponentially in M. What does this mean? That as we are sending, so first we send the system size to infinity, then as we are sending the Magnon sectors to infinity, it will take exponentially long times to empty M spins, so all states with M down spins from our system. And physical consequence of this is that basically the dynamics will be almost frozen in the regime where these bound states exist. So what we usually expect in this system, because in integrable systems we have quasi-particles which propagate ballistically throughout the system, let's say that we have a spin chain. Here we're inserting the particles or taking them out. What will happen, because here we're exciting something, is that we'll see this light cone structure, because it's propagating ballistically the excitations. But instead, if we go to the delta larger than 1 regime, we see that the dynamics is more or less confined very close to the boundary. And if we look at how much magnetization is flowing out of the system, we can see that for delta smaller than 1 regime, the decrease of magnetization is linear with time, and for delta larger than 1, basically magnetization decreases logarithmically with time. And this is, again, as I explained, a consequence of boundary bound state, because it takes exponentially long times to empty M down Magnon, all of the M down Magnon states from the system. Furthermore, we can look at the dynamics of the spin at particular sites and just plot the decay rates of the boundary bound states, and we see that the dynamics of the spins follows very closely the dynamics of the leading decay rates. Okay, so let me move to the outlook. So the first problem is that we don't know what the eigenstates are. We just have a upper triangular structure. So the question is, could we devise some integrability-based method to also get the corresponding eigenstates? The second question is, can we do hydrodynamics of these systems? And this is work in progress and seems that it's actually quite easy. So the third question is quite concrete. So when we were looking at the spectrum of the system that I just presented, so XXZ with a single boundary loss, we observed something interesting. Namely, there is a formation of bands in Liouville spectrum. So real part of lambdas tells us how fast the things will decay, and it seems that basically the eigenstates are separating into three different regimes which have different speeds of relaxation, and between them there are bands which we were not yet able to explain. So then the fourth question is to examine the physics of other models, because it seems that there is a lot of non-trivial things happening already in this simplest example, and as I presented, there are many other models that can be studied. And the final thing that I would like to point out is that there seems to be important physical implications of boundary bound states. This was observed also, for instance, in KPZ equation on half line, where the polymer KPZ equation also describes polymers, and the polymer deconfinement transition, where on one side of transition polymer is confined to the boundary and on the other side is deconfined, was also related to bound states. So with this, I would like to thank you for your attention and welcome any questions.
One question. If I get it right, so the dynamics of your system depends on the existence of a bounded state.
Yes.
It makes me remember, like, for example, the Annecy chain, where you have a topological or not topological state, wherever the spin is half integral or integral. Mm-hmm. And correspondingly, you have a bounded state on the chain when it is topologically in a topological state. So
okay.
Does this effect, even not even, can be manifest at the dynamics?
Maybe. I'm not sure. We haven't checked for spin 1 what happens, but well, yeah. I mean, that's a good question. I don't know.